Hey guys, what's up? Welcome to today's video. We're going to be starting ionic bonding. It's going to be today's a very simple, kind of even a short video, just getting started in ionic bonding. It might even be stuff that you did in biology, some of it, but these are just the basics. It should be nice and smooth today, nothing too complicated. Today, I am going to ask you to do one thing, and that is I really need you to take good notes today. I think your notes today are going to be very pretty, maybe not as pretty as mine, but your notes should be very pretty today because it's very important that you write stuff down. It involves more of your brain when you write things down. If you've ever introduced yourself to somebody and they tell you their name and 2 seconds later you forget it, it's because it didn't involve enough of your brain to stay stuck in your memory. If you actually listen to something and then remember it and then write it down, you're seeing it, you're writing it, it's actually going through different sections of the brain when you're writing stuff down. That is literally why you remember things better that you write them when you write them down. So please take good notes today. It will help you remember this. Again, this is a really basic introduction of ionic bonding, so should go nice and smoothly. If you have any questions or you're confused on anything, reach out and we'll get back to you. All right, without any further ado, let's get started. Welcome to Ionic Bonding. Not my best joke. Don't love the joke, but it's the joke that I'm going with. So let's jump in and get started. First thing I want you guys to do is to draw the Bohr models for sodium and chlorine. Right next to each other would be fantastic. Bohr model, protons, neutrons, electrons. Show me them clearly in your notes. The sodium on the left, chlorine on the right. I'm going somewhere with this. It's not just a review of Bohr models. So please take a moment, pause the video, and draw the sodium and draw the chlorine next to each other. If you've done that correctly, it should look something like this, where the sodium has 11 protons, 12 neutrons, and 2, 8, 1, and the chlorine, of course, has 17, 18, 2, 8, and 7 in the outside shell. Now, if I asked you, is this sodium stable? You would, of course, say to me, no, it's not stable. That sodium is not stable because it doesn't have a full valence shell. The outer shell only has 1 electron, so not stable. Which is correct, right? That sodium is not stable because it does not have a full valence shell, and it's got that 1 electron, and it's very sad, and it really wants to have a full valence shell, and gosh, if only it could get rid of that 1 electron, it would be really happy. And I could ask you if that chlorine is stable or not, and you would tell me, nope. Once again, not stable, wants a full valence shell. Because apparently that's how you look and sound to me. But of course, it's not stable. The chlorine is saying, oh no, I'm really unstable. If only I had 1 electron, if only somewhere I could get an electron from. And of course, this is a throwback to the octet rule that tells you that atoms are most stable when they have a full outside valence shell. So we're going to be referring quite a bit to the octet rule, maybe not even referring to it, but we're going to be just using it to justify how to make atoms happy. So we've got a sodium saying, I'm so sad, I want to get rid of an electron, and a chlorine saying, I'm so sad, I wish someone would give me an electron. And as you can imagine, what's going to happen? You got it. The sodium is going to give the electron to chlorine. So in order to be happy, the sodium is going to give that electron to chlorine. And this makes them both happy. This makes them both stable. This makes them both have full valence shells. And now they are both just thrilled because they've got that full outer valence. Very easy solution. Sodium loses the electron, gives it to chlorine. Chlorine says, thank you very much. Sodium has 8 in the outside shell, full octet. Chlorine has 8 in the outside shell, full octet. Fantastic. And as you can see, sodium has lost an electron, and that will make it a +1 ion, because when you lose an electron, you become a +1 charge, because there are 11 positives in the nucleus and only 10 negatives out here, so that's going to leave you with a net charge of -1. The chlorine has gained an electron and become a -1 ion, because it started out with 17 electrons and 17 protons, and now it has 18 electrons, and that makes it a -1 chlorine ion. And if you remember, when something has a negative charge, when a non-metal has a negative charge, we call it an ide, right? We end the atom in ide. We change the ending to ide. So this is not a chlorine ion, it is a chloride ion, because we have gained electrons and made that stable.
That's so important, I'm going to say it again. The sodium atom has one valence electron, doesn't want it, wants to get rid of it, loses that electron to become a +1 sodium ion. The chlorine atom is unstable, wants to gain an electron, gains one electron, becomes a -1 chloride ion, once again, to get that full valence shell.
So now I have a sodium ion, a +1 sodium ion, and it's just hanging out over here. It's very happy, it's very stable, got that full outside shell. And this chloride ion is also very happy. And if we put these guys close enough together, of course, the positive will attract the negative, and the sodium ion and the chlorine ion will actually stick together. The positive, because we lost an electron, and the negative, because we gained an electron, ions will stick together. But of course, in chemistry, we don't ever just really do two atoms. There's never just two atoms. That would be way too small to even notice. We have many, many, many millions and billions of atoms. So if another sodium came along and it wanted to snuggle up, would it snuggle up next to a sodium? No. It would snuggle up here next to this chlorine, and it would stick right there. And if another sodium come along, maybe it would stick right here. And if another sodium came along, maybe it would stick right there. And actually, because this is three-dimensional, maybe there would be a sodium above the chlorine. Maybe there would be another one below the chlorine. And then where would this chlorine go? Well, this chlorine could come over here, and it could actually stick right there. Or another chlorine could come over here, and it could stick, wow, I could stick to two sodiums. I could stick right there. And another one could come along and it could stick right here. And so you kind of see that we're going to get this repeating pattern where every sodium ion is going to stick to chlorine ions, and every chlorine ion is going to stick to sodium ions. So in your notes, I always recommend doing a 4x4 lattice, and we'll get to that in a second, of sodium and chlorine. I think that gives you a good idea of what you are going to be seeing. So you have a sodium stuck to a chlorine, stuck to a sodium, stuck to a chlorine, and just kind of complete this here while I complete this. Of course, because I have a smartboard, I can go a little bit silly with it. This is probably what you should have in your notes, but once again, I can get wacky. And of course, this could keep going. This could keep going in that way for 1,000,000, and it could keep going up for 1,000,000, and it could keep going left for 1,000,000, and it could keep going down for 1,000,000, and it could even come towards you and go away from you and actually make a very, 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 very small crystal of salt. And that is what we see when you have a little grain of salt. A little teeny tiny grain of salt is this structure right here, repeating over billions and billions and billions and billions of times. This repeating structure is called, has a few names. It is called a crystal lattice. You could also call it an ionic salt. In fact, you could actually take any of these four words right here and write them in basically, pick any two of them and in that order. So you could call it an ionic salt. You could call it an ionic crystal. You could call it an ionic lattice. You could call it a salt crystal. You could call it a salt lattice. You could call it a crystal lattice. Any of those are totally fine. As long as you say two words in that order, you're going to be great. And this is, once again, here are some pictures, this repeating plus, minus, plus, minus, plus, minus, this repeating plus, minus, plus, minus, plus, minus. This crystal lattice here is what happens when you get salt crystals. Now, if you have a couple of bazillion of them, they might form something like that. And if you go even bigger, you can have very, very large salt crystals that are even a few inches big. that you can get and you can see. So all of this is just these repeating ions, positive stuck to negative, in 3 dimensions to get this crystal lattice. So if we really think about it, ionic bonding has 2 separate parts. The first part is when we make the ions, when electrons move around to make the atoms stable. That's what we first talked about. The sodium didn't want the electron, gave it to the chlorine. Now everybody's happy. But they are positive and negative ions. And these positive and negative ions stick to each other. And the sticking of the positive ions and the negative ions together, the ionic sticking, is really what we call ionic bonding. Why is it called ionic bonding? It's called ionic bonding because this is a really easy one. It's because ions are bonding. Ions are sticking together. In order to name ionic compounds, it's fairly straightforward. We just need to remember that any nonmetal is going to change its ending to "ide." Any nonmetal ion, once it forms an ion, is going to change that ending to "ide." And then all you do is you say the metal and the nonmetal. So the metal, then the nonmetal, changing the ending to "ide." So in the example that we provided, of course, it was a sodium and a chlorine. Change it to "ide." So it's sodium chloride. Always the metal first, the nonmetal, and then "ide." Alrighty, so now let's take it one step further and try 2 different but similar atoms. And we can try potassium and we can try fluorine. So please, on the left, draw potassium. On the right, draw fluorine. Draw those 2 atoms. Take a moment, probably pause the video. Go ahead and do it though, because I want you guys to see exactly how this all works. This is obviously what you should have gotten. No real explanation needed, except to say, wow, this potassium is a little bit grumpy. This potassium is a little bit grumpy because it does not have a full valence shell. This potassium really wants to lose an electron. And this fluorine right here is grumpy as well. The fluorine is grumpy because it does not have a full valence shell. It really wants to gain an electron. And it's really no secret, if we put a bucket of these together, that this electron right here would leave the potassium, yay, and it would go here, and this shell would be empty, and now potassium would be stable, fluorine would be stable, and everything would be happy. So, of course, we end up with potassium fluoride. The potassium has lost an electron, the fluorine has gained an electron, potassium's +1, fluorine's -1. Yes, they're going to stick together. Yes, you're going to get some huge crystal lattice. Yep, it's going to be this repeating structure of K's and F's repeating each other, making this nice, beautiful salt crystal. And just like sodium chloride, we can get a little more complicated. I promise you, this one's not going to work as smoothly. Take a moment to draw lithium. Take a moment to draw sulfur. And then my question, if you were sitting in front of me, would be, what's wrong with this picture? You have to draw it to see it. Something's going to be wrong. Well, if we had a bucket of Li and a bucket of S, this Li right here wants to get rid of an electron, and this S wants to gain an electron, gain 2 electrons. Look, it's got spots for 2. So if I move this here, we have not solved the problem, because sulfur is still unhappy. Yes, lithium is happy, but sulfur is still unhappy. So what we're actually going to need to do is we're going to need to get another lithium to make everything happy. And now this electron can go here, and this electron can go here, and it actually takes 2 electrons to make the sulfur stable. So this electron goes there, this electron goes there, and we end up with lithium sulfide. And the formula would be Li2S. Why do we need 2 Li's and 1 S? Well, because the sulfur had 6 in the valence shell, and the lithium had 1 in the valence shell, and so you needed 2 lithiums to make the sulfur happy. Li2S, well, couldn't I just do that with one of the ones before? Couldn't I just do that with potassium? Can I just make this K2F? No, you can't make this K2F, because the K is giving away one, the F needs one, so this is going to be a 1-to-1 ratio. It's just going to be KF if I was writing the formula. For lithium and sulfur, the formula is going to be Li2S because I need 2 lithiums to make that sulfur happy, to make all of the shells be full shells, right? Of course, we remember that the lithium is stable with 2 in the first shell, so they're both stable, and the sulfur is going to be happy with 6, 7, 8 in that outside shell. So we're going to make lithium sulfide, and it's going to be Li2S. Next challenge. Similar problem, but different. Be and F. Take a moment, pause the video, draw Be, draw F. If you can pause the video, and you can draw Be, and you can draw F, and you're like, I got it, then you got it. If you don't, then you don't got it. Try and take a moment, pause the video, draw Be and F next to each other, and see what happens. Okay, we got a problem. Be really wants to get rid of 2 electrons, or gain 6. No, it's not going to gain 6. It wants to get rid of 2 electrons. But if Be gives one of its electrons to fluorine, yay, fluorine's super happy, everybody wins. No, everybody does not. The Be is not happy right now. So what do we got to do? We're going to need another fluorine. So if I have another fluorine, now we've got the opportunity to make everybody happy, because this guy is going to go run over here, and that fluorine's happy. And this guy is going to go run over here, and this fluorine is going to be happy. And the beryllium is going to be happy as well. So everybody will be happy when the beryllium gives 2 electrons away. It gives 1 to this fluorine, 1 to this fluorine to make it a fluoride. We end up with beryllium fluoride, and the formula is BeF2. We needed to do this to make sure that everybody was stable, to make sure that everything worked, to make sure that all those valence electrons were either emptied to be a full valence shell underneath it, or filled to have a full valence shell. So of course, you're going to call it beryllium fluoride, and the formula is BeF2. 1 Be and 2 Fs to make everybody happy.
So I'm going to stop right there. I think that is a perfect little taste of ionic bonding, just the very beginning. Everything that I did today is very basic. This is as simple as I could make it. I tried to make it as clear as possible. You should have no issues with. If there's anything that you was a little bit, I didn't really understand, you need to go back, because this is as basic and simple as it gets in terms of ionic bonding. Make sure you understand how to name, make sure you understand how to write that formula, make sure you understand what the electrons are going, always from the metal to the non-metal, and why the atoms are sticking together, and you should be great. I expect this lesson was very, very easy for you to understand. If there's any issues you have, reach out and talk and ask. Other than that, I'm going to say, have a great day.